Hello guys, welcome back to my channel. I'm Shams Fatima from Sri Venkateshwara College of Engineering, Bangalore. So today my topic is approaches to the integration testing from the subject software testing. Approaches to the integration testing involves functional decomposition, call graph and the paths. The functional decomposition involves top-down, bottom-up, sandwich and Big Bang theory. Call graph involves pairwise integration, neighborhood integration, and the paths involves paths and atomic system functions. Basis of integration testing strategies. So the functional decomposition applies best to procedural codes, and the call graph applies to both procedural and object-oriented codes. paths is applied to both procedural and object-oriented codes. So let's take the example of calendar program. So the calendar program involves the date in the form of month, day and year. The calendar function has the date of the next date, our old friend's next date. We very well are aware about the next date problem, which consists of month, date and year. The day of the week corresponding to the date, the zodiac sign of the date, the most recent year in which Memorial Day was celebrated on May 27th, the most recent Friday, the 13th Friday. So let's have a look at the functional decomposition of calendar in the form of flowchart. It consists of the leap year, weekday, get date, zodiac, next date, Friday 13th and Memorial Day. The first step to the top-down integration. Gray units are the stubs that return the correct values when they are referred. This level checks the main program logic. The weekday stubs. The procedural weekday stub consists of month, day, year. Day name. If month is equal to 10 and the days are 28 and the year is 2013, then day name is Monday. And if month is equals to 10 and day is equal to 30 and year is equals to 2013, then day name is equal to Wednesday. And if the program is done. Top-down integration mechanism. Breadth first travels of the functional decomposition tree. The first step, check the main program logic with all call units placed by stubs that always return correct values. Move down to the one level, replace one stub at a time with actual code, and any fault must be in the newly integrated units. So now let's move ahead to the bottom-up integration mechanism. Reverse of top-down integration is the bottom-up integration mechanism. Starts at the leaves of the functional decomposition tree. Driver unit. Call next level unit serves as a small test bed. Drive the unit with inputs. Drivers know expected output. As with top-down integration, one driver unit at a time is replaced with actual code. Any fault is most likely in the newly integrated code. Now let us look at the top-down and bottom-up integration part together. Both depends on throw-away code. Drivers are usually more complex than the stubs. Both test just the interface between two units at a time. In bottom-up integration, a driver might simply reuse the unit level test for the lower unit. Fan in and fan out in the decomposition tree results in some redundancy. So this is the flowchart, which consists of start point of the bottom-up integration. It again consists of the year if it is leap, weekday, get day, zodiac, next date, Friday as 13 and memory. So let's move into the next topic, that is sandwich integration. It is the combination of both top-down and bottom-up integration system. It avoids some of the repetition on both top-down and bottom-up integration. It can be understood by the depth-first traversal of the functional decomposition tree. A sandwich is the one path from where the root to a leaf of the functional decomposition tree. It reduces the stub and the driver development. It is more complex fault-based isolation. This is the flowchart, which represents the sample of sandwich. It consists of both top-down and bottom-up approaches. So this is the Big Bang theory. So Big Bang integration is totally based upon the universal theory. It has no drivers, no stubs, and no strategies. And it is very difficult for fault isolation. It is named after one of our famous theory of the origin of the universe. So this is the practice in an agile environment with a daily run of the project. To the point. So let's have a look to the pros and cons of the decomposition based integration. Pros: it is intuitively clear, built with proven components, fault isolation varies with the number of units being integrated, and the cons are based on the lexicographic inclusion. A purely structural consideration: some branches in a functional decomposition may not correspond with the actual interfaces. Stubs and drivers development can be extensive. And the next topic is call graph based integration. So let's look into the definition. The call graph of a program is a directed graph in which the nodes are units, edges correspond to actual program calls or messages. Call graph integration avoids the possibility of impossible edges in the decomposition-based integration. It can still use the notation of stubs and drivers, and it can still traverse and call graph in a top-down or bottom-up strategies. So this is the flowchart with calendar program using a call graph strategy. So now let's look into the new topic, that is path-based integration, an integration testing level construct similar to the DD paths for unit testing. It extends the symbiosis of spec-based and code-based testing in the integration level. Greater emphasis on behavioral threats, shift emphasis from the interface testing to the integration among the units. Now let's learn about paths. It's message quiescence. It's a non-trivial path. There is always at least one point at which no further messages are sent. In the example of path, unit C is the point of message quiescence. In a data-driven program such as next date, month paths begin and end in the main program. In an event program such as Saturn windshield wiper, paths begin with a unit that senses an input event and then end in the method that procedures and produces the corresponding output events. So let's have a look at the cyclomatic complexity. The formula for the strongly connected directed graph applies because the messages always returns to their sending unit. We always have exactly one connected region, so we use the formula Vg is equal to edges minus nodes plus 1. So let's have a look at the comparison of integration testing strategies. Strategy basis: it's the ability to test the interfaces, ability to test the core functionality, fault isolation and resolution, and the second topic is functional decomposition. It's acceptable but can be deceptive, limited to the pairs of unit, good to the faculty unit, and the call graph. It's acceptable in the ability to test the interfaces and limited to the pairs of unit. It's good to a faulty unit. And the last but not the least one is the paths. It's excellent in the ability to test the interfaces, and it completes the test for co-functionality, and it is excellent to the faulty unit execution paths. I hope you got some information from my video. If you like my video, please do like, share and subscribe to my YouTube channel. Thanks for watching my video. See you guys in the next session. Bye guys.